talk about what it means to be the area underneath a curve. We'll start by looking at the region of a graph that is bounded by these four equations. So we have the parabola x squared plus 1, the horizontal line y equals 0, and the vertical line x equals 0, and the vertical line x equals 1. So let's look at that yellow region right there. If we wanted to talk about that area right there, here's that shape a little bit more blown up. We don't have a nice formula that we can use to be able to evaluate the area of that odd-shaped thing. It's not a nice triangle or rectangle or circle that we have an area formula for. So how do we talk about that area? Well, in a second we'll get to that, but let's talk about what the area of itself means. Well, if it was like a rectangle and we were going to take the length times the width, then we would be taking the x units times the y units. Now, if x and y were both measured in meters, well, then the area would be meters squared. And those are terms that we're used to when we're talking about area, like square feet and things like that, square inches. But what if x actually represented time and y actually represented velocity? So now when I took my x units, which is time, and my y units, which is now distance over time, when I would multiply them together, then the area I'm looking at would actually represent distance. So area under a curve doesn't necessarily represent something that we're used to in terms of area of a rectangle where it's, square inches or something of that sort. So now let's go back to talking about the area of that shape, which again, we can't actually calculate because we don't have a nice formula. So what we can do is we can approximate the area under that curve using shapes that are easy to calculate the area of, like rectangles, because rectangles are just height times width. So what if we use two large rectangles? So if I filled this weird shape thing here, that whole thing that I had in yellow on the previous slide, and I filled it up with two big rectangles, you can see that this purple is a good chunk of that area, but we are missing some that's here in the gray. So what we can do is we can calculate the area of this rectangle, which its height is 1, and its width is 1/2. So we can do 1 times 1/2 to get the area of this rectangle. And then we can take the area of this rectangle, which its height is 5/4, and its width is 1/2. And we can add those two areas together to say, all right, the area under this curve right here, bounded by these lines right here, is about 1.125. But that was two rectangles, and again, I'm still missing some of that area, so it's not enough. What if I did three rectangles? Well, as you can see, the purple is shaded a little bit more, so I have more purple here and less gray, but it's still not enough. I can do the same thing where I will calculate the area of those three rectangles. So the area of the first rectangle, height times width, second rectangle, height times width, third rectangle, height times width, to get an approximation of about 1.185. It's still a little bit closer to the actual area of this object, but there's still some gray that's missing. So what if we did four rectangles? So then I could take the area of the first rectangle plus the second plus the third and plus the fourth to get an approximation of about 1.219. As you can see, I have more purple and less gray here. I could do the exact same thing and use 10 rectangles. And as you can see, I have a whole lot more purple and a lot less gray. And when I do that, I get an approximation of about 1.285. So I'm getting closer to the actual area under the curve, but you can see I'm still missing some here. So notice all these four examples with the two rectangles, 3, 4, and these 10, they're all under approximations of the area. And each one of these rectangles, the left-hand corner is touching the graph. So it's this left-hand corner that I'm using for the height, this is the function evaluation right here, because notice these left-hand corners are on the graph of the function x squared plus 1. Now, what if I actually shifted them and I put these right-hand corners up on the graph? So what if I made the right corner be what touches the parabola? So with two rectangles, it would look like this. And notice the right-hand corner is what's touching. So now I've got the dark purple. It covers the entire area under the curve, but now I have this light purple extra stuff. So I can do the same thing. Now the height of this first rectangle is 5/4 times the width 1/2, plus this height is now 2 of this rectangle times the width of 1/2, and I get about 1.625. So now this is a little bit of an over approximation of the area because I've got the whole area plus a little bit more. Now this light purple, this extra stuff, if I use 3 rectangles, it's a little less. I have less of the light purple stuff, a little less of the extra stuff. I can calculate the area of those 3 rectangles, add them together to get an approximation of the dark purple, about 1.519. Now what happens if I use 4 rectangles? Then I have less and less of this extra light purple stuff, and when I calculate that area, I get about 1.469. If I were to use 10 rectangles, as you can see, a lot less of the extra light purple. But all of these last 4 examples were all over approximations, where the previous 4 examples were all under approximations. And as you've noticed, though, in both situations, more rectangles is going to be closer and closer, a better approximation of that area. We're going to get closer and closer to the actual area. So ideally, we could do 20 rectangles, 30, 40, 100, 50,000. And the more rectangles we use, the more of this area is going to, of this extra area, that's going to be less and less and less. So how do we apply this idea to any curve on a closed interval from A to B? So here I was blocked from 0, here 0 to 1, so I was focused on the area above the x-axis and located between 0 and 1. How do I apply this to any curve from A to B completely? So for the area under a curve y equals f of x on an interval A to B, we're going to need n rectangles. So we could have n is any number of rectangles, 2, 5, 1,000, it doesn't matter. These are the 4 things we need to do. Number 1, we need to define the base of those rectangles. The base is going to be the width, the bottom of those rectangles. We need to define the height of those rectangles by using function evaluation there. You know, the rectangle went up and it touched the parabola, so we got to go up and touch f of x. And then based on these bases and these heights, height times base would give us the area of each of those rectangles. So we would calculate all those areas of those little rectangles, add them all together, and that would give us an approximation of the area underneath that curve. So here you can see, going from A to B, one corner or some part of the rectangle is touching the function. That gives us the height of each of these rectangles. We've got the width of each of these rectangles, calculate the area of each of those rectangles, add them up, and we would get an approximation of the area underneath that curve. So we're going to talk about approximation by rectangles using partitions. So what is a partition? For a y equals f of x on a subinterval a comma b, we need to partition the interval into n subintervals. So I'm going to take this big area where I'm blocking off, right? I'm looking from A to B here, and I'm going to give these little subintervals. So I'm sectioning off little chunks of my big area here. And that little subinterval, those will form all the little bases of my rectangles, and you can make them as wide or as narrow as you want to. So to make n subintervals, to have n little subintervals, little bases of your rectangles for n rectangles, then you're going to need n plus 1 values of x. So you've got a, where you're starting, we'll call that x sub 0. And then you've got from x sub 0 to x sub 1 is one little section, x1 to x2, x2 to x3, x3 to x4, all the way up to xn. And so then that'll give us n of our little subintervals, where xn is actually the ending value b, the end of that interval. So each subinterval, you've got a subinterval from x0 to x1, from x1 to x2, x2 to x3, x3 to x4. So all your subintervals are from xi minus 1 to xi. And they have a width. You can find the width by just taking xi minus 1, subtract that, and that'll give you the width of that interval. And that's going to be the width of the base of the rectangle. So if the partition is called delta, that's what we typically call a partition, we give it the name delta, then what we refer to as the norm of the partition is going to be the largest delta x, largest delta xi, the largest of the differences or the widths of these intervals. And this is how we mathematically write it. Norm is like it kind of looks like absolute value twice. It's kind of what that looks like. And that's called the norm of the partition. And again, it's the maximum of all your delta xi's. It is really common to use what's called regular partition or uniform partition, where the subintervals all have the same width. So the examples that we had done previously, all of our rectangles, we divided it evenly so all the rectangles had the same width. And so we typically do that. In that case, every delta xi would be the same, so we could just call it delta x. We would find it by taking the end of the interval minus the beginning of the interval and dividing it by n. And then that would be the norm of the partition as well, because the max of all the widths, since they're all the same, they would all be the same max, right? And then all your xi's you can find by a plus I times delta x. So for a, which we said a was x0, so I is 0, x0 would be a plus 0 times delta x. And 0 times anything is 0. This term goes away, so x0 equals a. And then the next x1, I would just, starting at a, or x0, add that width of that partition, and that would give me x1. Add another one, it would give me x2. Add another one, it would be x3. So x3 is 3 deltas, x's, away from a. So it's starting at a and then going a plus 1, 2, 3 widths. So that's where this formula right here comes from. And now we need to find the height of our rectangles. So our height, we need some sort of a sample x value in the interval, in the subinterval, that we plug into the function to get the height. Now, it could be your left endpoint right here, which is the first set of examples we had done. It could be the right endpoint of your subinterval, or it could even be the midpoint. But you need some sample x value in every little subinterval to plug into the function to get the height of your rectangle. And again, it could be the left endpoint, the right endpoint, or the midpoint. Now you calculate the areas, right? You've got your width, which is delta xi. You've got your height, which is the function evaluation at some sample point in the interval, and then that's going to give you the area of that little rectangle. Add up all of those rectangles, right? Take all those rectangles, sum from 1 to n of each height times each width, and that's going to give you an approximation of the area underneath the curve. This right here is what we refer to as a Riemann sum. Now, more rectangles, you're going to have a much better approximation. If you could potentially have infinitely many rectangles, well, then that would be the entire area under the curve. But we know that's not possible. But we have talked about looking at the idea of something increasing positive without bound or approaching infinity. So what if the number of rectangles approached infinity? So we would talk about a limit as n was approaching infinity. So the area under a curve with uniform partition, f of x has to be a continuous non-negative function on the closed interval ab. Then we can define our partition as follows. A is equal to x naught is less than x1 less than x2 all the way up to b. Xn is equal to b. So that's taking that big interval and breaking it up into smaller subintervals. Each xi is found by a plus I times your delta x, where we're going to choose uniform partition, so delta xi would be b minus a over n for all I. And then x star is any value inside each of those subintervals that you'll plug into the function to get the height. And so then, if we take, these are the heights of all of our little rectangles and the widths of all of our rectangles, and we add them all up, right? Add all the sums of those rectangles up. As n approaches infinity, that would give us the actual area underneath that curve. So hang tight, we'll be back to do an example.